This is Desmond Parker again with A Plus College Ready and our final video for this series. Today we'll be talking about intramolecular bonding and intermolecular forces. Now, it's very important for us to know that there is a big difference between intramolecular bonding and intermolecular forces. Intramolecular bonding are the things that we already know. These are our standard ionic and covalent bonds. Remember, if you've forgotten, which I hope that you haven't, that our ionic bonding are due to electrostatic forces between metals and nonmetals, versus covalent bonding occurs between nonmetal atoms, and it consists of sharing of valence electrons. Remember, our covalent molecules will form either double, single, or triple bonds with one another. One type of intramolecular bonding that we have going on is a type of covalent bond which is extremely strong, and this is our network covalent solid. Network covalent solids are things like diamonds and graphite and silicon dioxide and fullerenes, which the only ones that you really need to know are the diamonds and the silicon dioxide. Those will probably be the only two that I can think of, and I might be wrong, that I believe that will show up on your exam. Covalent network solids, these guys have extremely high melting points, up in the thousands. They tend to be very hard on the Mohs scale of hardness. They typically have one of the highest values that you can get. And these materials do not conduct electricity, just like most covalent molecules. Now, graphite probably might be one of the exceptions to the rule when it comes to conducting electricity, is that we do have carbon nanofibers, which can be used for purposes of conducting electricity. Now, the big thing that we're going through is intermolecular forces, commonly abbreviated Imfs. Now, intermolecular forces are attractive forces between molecules. So think like an interstate, like I-20 or I-65 or I-10. It takes you between states. So intermolecular forces between two different molecules. So these are not covalent bonds. These are not ionic bonds, which happen in a molecule. These are interactions that happen between two completely different molecules neighboring each other. These are not bonds. You have to get through this through your head. These are not bonds. These are interactions, forces of attraction that are there. So, intermolecular forces. The intramolecular forces determine chemical properties. Intermolecular forces, or your IMFs, they determine every physical property that your molecule has. Every single physical property are because of intermolecular forces. So here's a list. You guys can read this. I'm not going to insult your intelligence by reading it to you. But these guys determine how those molecules will behave. They determine why water is a liquid at room temperature versus some other substance like methane, which is not. So we also have specific heats of substances which are based around intermolecular forces. Water has a very, very high specific heat because it has very strong intermolecular forces between them. So our first intermolecular force we're going to talk about, and this one right here can be a bit deceiving because it's called hydrogen bonding. It really should be better called interaction, because that's what it is. And this is what we call a very strong dipole interaction that's occurring between molecules. Now, when we have hydrogen bonding, you must at minimum have a hydrogen present. So if there's no hydrogen bonding can occur. Now, it's not just simply saying there's hydrogen there. We have to have fluorine, oxygen, or nitrogen attached to that hydrogen. If you have no oxygen, fluorine, or nitrogen attached to that hydrogen cannot and will not hydrogen bond. Now, if you have what I like to call FON attached to a hydrogen, it will interact with another oxygen, fluorine, or nitrogen on another molecule. But that, again, is only if that hydrogen is attached to a fluorine, oxygen, or nitrogen. So those molecules are highly electronegative. They're some of the highest electronegative values that we have on our electronegativity table. So they create what's called a partial positive charge on the hydrogen. Because hydrogen only has one electron, it exposes that proton on the other side, which will make that molecule slightly negative or slightly positive. And since that oxygen, fluorine, or nitrogen has now gotten that electron because it's now polar, it has an overall partial negative charge on it. So again, hydrogen bonds are attractive forces, not real bonds. Hydrogen bonding is what holds your DNA together. So one hydrogen bond is not very strong. But when we get a whole heap of hydrogen bonds together, we can hold two big old strands of DNA together. And it's hard to tear them apart because that hydrogen bonding is so strong. So when we get a lot of hydrogen bonding, we get a very, very strong attractive force between two substances. Hydrogen bonding is also what helps draw waters up through xylem and phloem in your trees. Hydrogen bonding also is what determines the state of matter of water. So, once we provide enough energy to overcome those forces of attraction, we can take our ice to water and add some more energy. We take our water to gas. When we sweat, this is a big one. In order for that water molecule to evaporate, it must get energy from the surroundings. So this is what we were talking about before a couple of lectures ago with endothermic processes, which absorb energy. So that absorption of energy will allow you to feel coolness because the water is literally taking the heat, and taking that heat away provides enough energy to overcome those forces of attraction between those between those water molecules. And as they evaporate away, they take heat with them in order to become a gas. Alcohol evaporation on your skin. This is another one. When you pour alcohol on yourself, it cools. Alcohol has hydrogen bonding in it. And again, providing it the energy to overcome that hydrogen bonding is what allows you to feel that cooling sensation. So the next thing is dipole-dipole forces. Now remember, our asymmetrical molecules have dipole forces, which one side of the molecule is going to be polar. The entire molecule is polar. One side is going to be partially positive. The other side is going to be partially negative. The more electronegative side will be negative. The side that's not as electronegative is going to be slightly positive. These molecules are going to orient themselves, which will allow them to interact with each other. And again, these interactions, just like with hydrogen bonding, don't last very long. They're very short interactions that happen, but there's a lot of interacting going on. And so this right here is a relatively stronger force. So hydrogen bonding is our strongest, then dipole-dipole is next. So we typically represent these with arrows. And this arrow will show the direction that the electrons are moving. So the side with the plus sign on it is the side that's positive, and the direction the arrows is pointing is the side that is more negative. And you will see this notation on a regular basis. This is just an example of these iodine and chlorine molecules lined up next to each other. In reality, does this happen exactly this way? Of course not, because these molecules are not stationary like in this diagram. But you can see with the green lines that these molecules are that's where the interaction is occurring. So remember, the iodine and the chlorine are bonded covalently, but they're also interacting with iodines and chlorines on another molecule. Ion-dipole interactions occur when we have water molecules which are interacting with ionic compounds. So your water molecule will orient itself around the ion in what we call a shell of solvation. And this shell of solvation will point in the direction of the charge. So if it's surrounding a positively charged ion, the oxygen, which is a partial negative, will face that that ion, and vice versa. If you're surrounding a negatively charged ion, then the hydrogens will be pointing towards the negatively charged ion. This is dipole interactions. So we have a gentleman by the name of Fritz London who discovered London dispersion forces. So simply put, all molecules have London dispersion forces regardless to whether or not they are polar. Our nonpolar molecules only have London dispersion forces. London dispersion forces are the weakest of the forces, and it is determined strictly by the number of electrons that your atom has. So the more total electrons, and we rarely count core electrons, but in London dispersion forces we do. One of the rare times which we really focus in on how many core electrons our atom has. Those core electrons do play a role in those interactions. So we have what's called polarizability, which basically is at one given snapshot, our atoms are on one side of the molecule, which will cause what we call an induced dipole moment. So an induced dipole moment can happen in a wide variety of ways. It can happen when you have a cation approach a non-polar molecule and it will induce a dipole, or you have a substance that has a dipole which will get near a substance that is non-polar and induce a dipole. So just like with water and oil, they are slightly soluble in each other because the water molecules can force an induced dipole. Now, we won't have much that goes into the solution. We don't have much that is going to go into that water, but we will have a few oil molecules which will have an induced dipole happen upon them and be able to become soluble in the water. Now, a vast majority of them, you can visually see that they don't. but there will be a couple that there will be a dipole that will be strong enough to be induced to cause them to happen. Dissolved oxygen in water. This is how fish breathe. So water molecules will form an induced dipole with the oxygen in the air. The colder that it is, the more oxygen that can be dissolved into the water, which is why there's an issue when plants dump, and I'm talking about power plants, dump warm water into rivers, because increasing the temperature prevents oxygen from dissolving into the water because the kinetic energy is too high. So as that kinetic energy decreases, the more oxygen will be dissolved into the water. So this right here is just a flow chart that you can use when you're trying to determine the type of intermolecular force that's happening. And it kind of helps you keep your thoughts straight. So I'm not going to insult your intelligence by reading it, but take the time, look through it, take it, and make sure that you understand it and understand how to use it. So let's take a look at this first question right here, AP level question. Which of the following is the strongest type of interaction that occurs between the atoms within the circled areas of the two molecules represented above? All right, so looking at this molecule, I would hope that you would see that we have a hydrogen attached to a nitrogen, and that this hydrogen is interacting with another nitrogen, and this hydrogen is interacting with that oxygen, which means that it should be hydrogen bonding. Now, going down here and looking at which one it is not, polar covalent bond. Those things are not bonded together, so polar and nonpolar covalent bonding can be eliminated. Because remember, it asks us strongest type of interaction between the circled areas. Those things are not connected to each other. And this is question 5, so this is fairly easy. Now, hydrogen bonding and London dispersion. Now, do these molecules have London dispersion forces? Yes, they do. But is that the strongest force that's occurring here? No, it is not. So that's why we should have hydrogen bonding. Which of the following molecules is least soluble in water? All right. Now, for solubility, as you saw in one of the earlier slides, it talked about having similar intermolecular forces. Will all of these substances dissolve in water? The answer is yes. They all will, but it's asking us about the one that's the least soluble. So water, I hope that you know that water is a polar molecule. It looks like this. Those lone pairs. You should know the structure of water like the back of your hand. So this means here that we have hydrogen bonding occurring. So this tells me that this right here is polar. This is a polar molecule. So we want to find which molecule basically is not polar. This molecule is polar, this molecule is polar, this molecule is polar. This one is symmetrical. So since that one is symmetrical, that means that it is nonpolar. So it is the one that is going to be the least soluble in water because it has symmetry. So it only has dispersion forces. So that was a quick overview of intermolecular forces. And as usual, if you have any additional questions, make sure that you direct them to your instructor. It has been a pleasure going through this unit with you. And I hope to see you all sometime in the future. And good luck as you continue. And I will talk to you all later.